So imagine trying to design like a functional city where billions of distinct buildings need to communicate with each other almost instantaneously.
Yeah, and the density of that city is just extreme.
Right. Like the entire metropolis fits on a tiny silicon square, basically the size of your thumbnail. And now you're tasked with drawing a single boundary line that divides this whole city exactly in half.
Which is a nightmare scenario for any engineer.
Totally. Because the rule is you have to sever the absolute minimum number of roads crossing that boundary. I mean, if you cut too many major arteries, the communication latency spikes, the heat density becomes unmanageable, and the entire city just collapses.
It just melts down.
Yeah.
Yeah, and that is actually the foundational engineering hurdle happening inside the very device you're using to listen to this deep dive right now.
Exactly. And that's our mission today. We are looking at this highly technical 2026 presentation. It's called Circuit Partitioning, FM, and Multi-Level Algorithms.
It's quite a mouthful.
It really is. But okay, let's unpack this. Because beneath that really intimidating academic title is, well, it's the blueprint for how engineers prevent impossibly large systems from basically choking on their own complexity.
Right. And while the source material is explicitly focused on VLSI,
Mhm.
that's very large scale integration, which, dictates modern computer chip design, the underlying math actually has super broad applications.
Wait, so it's not just for computer chips?
Oh, no, not at all. These exact same partition models are heavily utilized in distributed computing for load balancing across massive server clusters,
Okay.
and even in data science, like for community detection within massive social networks. We're fundamentally looking at algorithms that are designed to, fracture complexity into workable pieces.
Fracture complexity. I like that. So if we're going to fracture a circuit, we first need like a mathematical model to actually represent it, right?
Exactly. You need to draw the map before you can cut it.
Right. But standard graph theory just seems immediately insufficient here. Like, if standard graphs only connect two nodes via a single edge, they're kind of useless for modeling a physical wire on a chip.
Yeah, because a physical wire isn't just point A to point B.
Exactly. It might simultaneously connect, a processor, an I/O port, and like three different memory banks all at once. So I'm assuming engineers just have to throw out standard graph theory entirely and use some sort of multi-node model.
They do. I mean, modeling a circuit as a standard graph would result in massive data loss. You'd lose all the context. So instead, engineers map the circuit as a hypergraph.
A hypergraph?
Yeah, in a hypergraph, your standard edge is replaced by hyperedge, or what the industry just calls a net.
A net. Got it.
Right. And a single net can encapsulate any number of modules. So a 2-pin net acts like a standard edge, connecting two things. But a 20-pin net encompasses 20 different modules that are all operating on the exact same signal simultaneously.
Okay, so is a traditional graph sort of like a phone call between two people, while a hypergraph is more like a group chat where one message or one net connects five different people at once?
That is a perfect analogy, yes.
Uh-huh.
A hypergraph is exactly like a group chat. It perfectly represents the physical reality of the hardware.
But mathematically, hypergraphs are, notoriously difficult to process, right? I mean, you can't easily run standard matrix operations on sets that just contain random arbitrary numbers of vertices.
No, you really can't, which forces a crucial translation step. To actually make the math workable, the algorithms translate this hypergraph into what's called a bipartite graph.
Bipartite, so two parts.
Exactly. They split the data into two completely distinct sets of vertices. Set A contains only the physical modules, and set B contains only the nets.
Oh, interesting.
Yeah, and then edges are drawn strictly between set A and set B, never A to A, never B to B.
So it transforms this crazy multidimensional grouping problem back into a flat two-dimensional structure.
Right. Something a computer can actually iterate through rapidly. And if we connect this to the bigger picture, the entire VLSI design flow completely hinges on getting this bipartite graph partitioned correctly.
Because partitioning is literally step one.
It is step one. It dictates placement, clock tree synthesis, routing, timing closure. If you fail here, you basically guarantee congestion and timing violations way down the line.
Right, the whole domino effect. So the objective is clear. We need to divide this hypergraph group chat into, let's say, taller roughly equal blocks, while minimizing the number of nets that span across the different blocks.
That's the goal.
And to achieve this, The sources dive into this classic solution from 1982, the fiducia mathesis algorithm, or just the FM algorithm,
Yeah, FM is foundational. It's an iterative heuristic algorithm.
meaning it's not trying to solve the whole universe at once.
Right. It doesn't attempt to solve the NP-hard problem globally. It just takes an initial partition, basically a random starting guess, and systematically attempts to improve it by moving one single module at a time.
Just one at a time. And the metric driving those moves is called gain, right?
Exactly. Gain is the magic number.
So the math dictates whether moving a specific module across the boundary will actually reduce the overall cut cost. The source defines the formula as DEE text FSV. So gain equals the from side minus the to edge.
Let's contextualize that formula a bit. So imagine a module currently sitting in block 0. The from side represents the number of nets connected to this module that are entirely contained within block 0.
Okay.
So if you move the module, you're going to drag those nets across the boundary, which increases your cut cost.
So the from side acts as like a penalty. These are the internal ties you were breaking.
Yes, exactly. Now the to edge, conversely, represents the number of nets connected to the module that are currently sitting entirely over in block 1, just waiting for it.
I see.
Right. So if a module is tethered to, say, 10 nets in block 1, but only 2 nets in its current home of block 0, that FS minus TE calculation yields a highly positive gain.
Because 10 minus 2 is 8, positive gain. So moving it naturally untangles the hypergraph.
Precisely. The FM algorithm greedily searches for the module with the highest positive gain and just moves it.
Okay, but wait. Calculating the gain for like millions of modules and then recalculating all the adjacent gains every single time just one module moves, I feel like that should completely paralyze a processor.
You would think so, yeah.
I mean, the continuous sorting required to find the next best move in an array of millions, that's just computationally prohibitive.
It would be entirely impossible without a specific data architecture that they use, called the bucket data structure.
The bucket.
Yeah. It operates as a bounded priority queue. So instead of a massive flat array that requires continuous, slow scanning, the algorithm drops modules into specific buckets that are just labeled by their current gain score.
Oh, wow. So
Yeah.
it functions essentially like a dynamic leaderboard.
That's a great way to put it.
If a module's gain changes because, a neighbor moved, it just jumps to a different bucket.
It just hops over.
And the algorithm never has to actually search for the best move. It just blindly grabs whatever module is sitting in the highest value bucket at that exact millisecond.
Exactly. It guarantees an all-or-time complexity for finding the maximum gain.
Euler meaning it happens instantly.
Instantly. The operations happen in constant time, entirely independent of how massive the overall circuit is.
Okay, so that definitely solves the speed issue. But I need to push back on the actual mechanics of this FM algorithm, specifically the locking phase.
Ah, the locks, yes.
Right, because the documentation states that during a pass, once a module is moved, it is locked in place. And it cannot be moved again, even if its gain becomes highly positive later in the pass.
That is correct.
Wait, if we lock them, aren't we just stuck with the first decent move? By locking modules, we are intentionally crippling the algorithm's search space. It just seems like a guaranteed way to trap the system in a local minimum.
It's a very rigid constraint, I'll give you that.
Yeah.
But consider the alternative.
Okay,
Without locking, you introduce what's called thrashing.
flash.
Yeah. Imagine module A moves to block 1 because of module B. Well, now module B's gain shifts, so it follows module A over to block 1.
Okay, that makes sense.
But now module A's gain shifts back, and it returns to block 0.
Oh, I see.
The algorithm basically enters an infinite loop. It just oscillates the same highly connected modules back and forth forever without ever exploring the broader network topology.
Okay, thrashing definitely makes sense as a failure mode, but locking a module just forces a different kind of failure, doesn't it? I mean, you lock a bad move, which alters the gain of its neighbors, forcing a cascading sequence of like suboptimal moves. The algorithm just marches blindly down a terrible path.
It does march down that path, but here's the trick. It records every single step,
Oh.
and that is the defining characteristic of the pass system. FM doesn't just stop when the gains turn negative. During a pass, it will intentionally execute moves with negative gain, moves that actively worsen the cut costs.
Wait, really? So it's essentially climbing out of the valley just to map the surrounding hills?
Exactly. It forces every single module to move exactly once. And once the pass is complete and the entire landscape is mapped out, the algorithm reviews the chronological history of the cut cost.
Okay.
It pinpoints the exact move that resulted in the lowest overall cost. And it just rolls the entire system back to that specific state.
That is
It
brilliant.
unlocks everything, recalculates the baseline, and initiates a brand new pass. And it just repeats this until a pass yields a peak improvement of absolute zero.
So it systematically explores terrible configurations to guarantee it hasn't missed a deeper minimum nearby. I love that. It's like a brute force topographical survey wrapped in a greedy heuristic.
That's exactly what it is.
However, the source material pivots pretty hard here. Because despite the efficiency of the bucket data structure, flat FM partitioning hits a hard scalability wall.
A very hard wall.
Yeah. When circuits surpass like 100,000 modules, the local minimums just become too vast for the past system to climb out of.
Right. Because the sheer dimensionality of modern circuits, which, by the way, easily house tens of millions of gates, it just renders flat FM completely obsolete. The algorithm just gets lost in the noise.
So we need a way to scale up.
Exactly. Which necessitates the shift to multi-level partitioning.
Multi-level.
Yeah. The framework operates in three distinct phases: coarsen, partition, and refine.
Okay, so what does this all actually mean? If FlatFM fails because the graph is too granular, coarsening must be the process of like artificially reducing the graph's resolution, right?
That's a good way to think about it.
Is coarsening basically like zooming out on Google Maps? Like instead of trying to divide a million individual houses or modules, we group tightly connected houses into neighborhoods and then we just divide the neighborhoods.
Yes. That is the mechanical reality of the coarsen phase. You absorb highly interconnected modules into single supernodes.
Supernodes.
Right. So a dense neighborhood of 1,000 logic gates gets mathematically collapsed into a single vertex. And by repeatedly collapsing these dense clusters, you shrink a graph of 10 million modules down to maybe a few thousand supernodes.
And at that macro scale, partitioning the graph using FM is probably trivial.
Exactly. It's incredibly fast. And once partitioned, the refine phase essentially just unzips the supernodes back to their original granularity, making tiny boundary adjustments along the way.
But wait, the efficacy of that entire pipeline depends entirely on how you define a dense cluster, doesn't it?
100%.
Because if you group the wrong modules together during the coarsen phase, you accidentally hide critical crossing wires inside a supernode, and the partitioner will literally never see them.
Which would ruin the partition.
Right. Now, the sources state the clustering is achieved through coarsening via matching, specifically looking for let me get this right, a minimum maximal matching.
Yes. And what's fascinating here is the mathematical tension in that terminology.
How's-
Well, a matching just implies pairing modules that share a net. A maximal match means you continue pairing independent modules until it is structurally impossible to add another pair without overlapping.
So you have covered as much of the graph as structurally possible. You leave no module isolated if it can be paired.
Exactly. That ensures the entire graph shrinks uniformly.
Okay, but why minimum? That sounds completely counterintuitive. You want a maximal match, but a minimum one.
Because there are thousands of valid maximal matchings for any given graph. The algorithm specifically hunts for the matching that yields the minimum possible cardinality, meaning the fewest number of resulting clusters.
Oh, because fewer clusters means.
It dictates that the clusters are denser, they encapsulate more highly connected modules. This aggressive contraction creates a vastly superior macrostructure for the FM algorithm to evaluate later.
Okay, the theory tracks perfectly, but how do you systematically find the sparsest maximal match without just brute forcing the entire graph?
Well, the sources detail a primal dual approximation algorithm to solve this efficiently.
Primal dual.
Yeah. Instead of randomly pairing modules, it assigns a dual variable, which you can think of as a budget, to every single net in the hypergraph. And the algorithm uniformly increases the budgets of all active nets at the same time.
A budget that increases until it hits some kind of threshold.
Precisely. Once a net's budget reaches its assigned weight, that net becomes tight.
Tight. Okay.
Right. And the algorithm immediately locks the modules on that tight net into a cluster and deactivates any neighboring nets to prevent overlap.
Wow.
By elevating these dual variables systematically, the algorithm mathematically guarantees a bounded approximation of the optimal minimum maximal match, completely bypassing the need to brute force millions of combinations.
It's just such an elegant way to let the topology of the circuit dictate its own clustering. But implementing this in software has to introduce severe memory constraints, right?
Oh, absolutely.
The documentation highlights this library, CKPTN-CPP, written in modern C++20, and it focuses heavily on optimizing the contraction pipeline. Because when you absorb modules into supernodes, you fundamentally alter the hyperedges connecting them.
You do. You introduce a massive influx of parallel hyperedges and self-loops.
Self loops.
Yeah. If two modules within a new supernode previously shared a net, well, that net is now entirely internal to the supernode. It's a self-loop.
Oh, I see.
Those are easily discarded, though, because they have zero impact on the cut cost.
Right, they don't cross any boundaries anymore. But parallel edges, those are the real computational threat.
Huge threat.
Like if you have two distinct nets connecting neighborhood A to neighborhood B and you zoom out, those nets now look mathematically identical. They're duplicate nets spanning the exact same supernodes.
Exactly.
And if you don't detect and merge those duplicates, the hypergraph doesn't actually shrink in complexity, which completely defeats the entire purpose of coarsening.
You're spot on. But detecting those duplicates is computationally punishing. To prove two nets are truly identical, you have to cross-reference their entire pin lists.
Which takes time.
Right. Across millions of contracted nets, this scales at a Joe Dunderlawler. It is a quadratic time complexity that will entirely bottleneck the CPU and stall the whole partitioner.
So to circumvent that quadratic bottleneck, the FICPT and UpCPP library deploys this really clever trick. A min-hash pre-filter for any nets containing between 6 and 200 pins.
Yes, the min-hash trick.
Instead of directly comparing the module arrays of two nets perfectly, it leverages hashing functions to map the modules into a fixed size signature.
It dramatically compresses the dimensionality of the comparison. So the algorithm generates a 64-element integer signature for each net.
Just 64 elements.
Yep. Because they are now fixed-size integer arrays, the CPU can rapidly estimate their similarity using very fast bitwise operations, rather than, iterating through these variable-length lists of modules over and over.
So it's estimating the Jacquard similarity, calculating the intersection over the union of the two sets. Exactly. And if the min-hash signatures overlap by an 80% threshold, the algorithm just assumes they are highly probable duplicates. And only then does it actually execute the expensive exact match verification.
Right. So it essentially bypasses that nasty AUDI2 operation for like 99% of the graph.
That is just wild. It's a critical software optimization that allows the theoretical math of multi-level partitioning to actually execute in real time. And, the library actually provides empirical data to validate this architecture.
Yes, the test runs.
Right. Here's where it gets really interesting. The sources document test runs using Yosis JSON inputs, which is an open source synthesis tool. And the empirical data highlights a severe behavioral shift depending on the constraints applied.
The KOA constraint specifically.
Yeah, take the sphere netlist circuit, 65 modules, 623 nets. When partitioned into 2 blocks by partitioning, the cut cost is 28. But when partitioned into 3 blocks, KOA partitioning, the cost immediately spikes to 85.
And that variance scales up with circuit size too. Like the Sphere 3-Hoff netlist, which features 188 modules, registers a bi-partition cut cost of 90. But when subjected to a 3-way partition, the cost escalates to 251.
Which seems highly counterintuitive at first glance. I mean, if you are fracturing a network into 3 smaller blocks instead of 2 massive blocks, the internal volume of the blocks is smaller, so you would expect fewer internal wires.
Right.
And potentially a more manageable boundary.
You think so?
So why does imposing a 3-way split cause the cut cost to nearly triple? Shouldn't smaller pieces mean fewer crossing wires?
This raises a really important question about the geometric reality of hypergraphs. You have to remember, a hypergraph is not some homogeneous grid.
Yeah, that's right.
It is a landscape of extremely dense logic clusters that are separated by very sparse data pathways.
Kind of like real cities separated by highways.
Perfect comparison. When you run a bipartition, the algorithm only has to locate the single deepest canyon in that topology. It finds the natural fault line where the communication density is lowest, and it just splits the design right there.
Oh, I get it. It respects the natural architecture of the network.
Yes. But K-way partitioning introduces rigid equilibrium constraints. If you demand 3 blocks of identical weight, the algorithm cannot simply follow the natural fault lines anymore.
Because the fault lines might not divide it into perfect thirds.
Exactly. To satisfy the balance constraint, it is mathematically forced to drive a hyperplane directly through the center of a dense logic cluster.
It's like being asked to cut a highly asymmetrical pie into 3 perfectly equal slices. The cuts have to intersect somewhere, and you basically guarantee that you're going to slice directly through the densest ingredients.
Yes, severing hundreds of localized connections in the process. The balance constraint fundamentally overrides the cut cost optimization.
Wow.
And it highlights exactly why multi-level coarsening is so critical. If you can encapsulate those dense logic clusters into supernodes before applying the K-way constraints, you physically prevent the algorithm from driving a hyperplane through them.
Because they're already locked together as a single node. That is brilliant. Okay, so to synthesize the whole engineering pipeline we've talked about today, we start with a staggeringly complex hypergraph that accurately reflects the physical wiring of a massive system.
Right.
And because standard flat FM partitioning just gets trapped in local minimums, we deploy a primal dual matching algorithm to coarsen the graph, mathematically ensuring we absorb those dense neighborhoods into supernodes.
We compress the complexity.
We compress it. We deploy min-hash signatures to deduplicate the hyperedges in constant time. We run the O1 bucket data structure to partition the macrograph, and then we refine it back to its original state.
It is an incredibly robust chain of logic designed to completely tame scale.
It really is.
And, it is vital to recognize that without this specific sequence of algorithms, the physical construction of modern processors would just be impossible.
Yeah, we wouldn't have the tech we have today.
Not at all. The capacity to efficiently partition a trillion transistor design is literally what prevents data pathways from congesting. It limits thermal output, and it allows sequential logic to synchronize at gigahertz frequencies. It is the hidden architecture of computational speed.
It is the invisible math governing the hardware we all rely on every day. But, the source material actually leaves a very deliberate breadcrumb right at the end.
Oh, the future directions section.
Yeah. It briefly lists ML-guided gain prediction as an active area of future research. Basically, machine learning models trained to bypass the FS minus TE calculations entirely.
Which is a huge paradigm shift.
Massive. I mean, if neural networks can be trained to intuitively predict the optimal hyperplanes simply by analyzing the graph embeddings, we might be looking at the end of static partitioning altogether.
It's wild to think about.
It really leaves this provocative concept for you to ponder: shape-shifting hardware.
Shape-shifting chips.
Yeah. If the computational overhead of partitioning drops to near zero through ML prediction, we could foresee processors that dynamically repartition and reroute their own physical logic gates in real time.
Wow.
Imagine a chip that physically restructures its internal neighborhoods millisecond by millisecond, completely optimizing its own architecture on the fly, depending on whether you are compiling code or, rendering a high-end 3D video game.
It's an entirely new paradigm of dynamic engineering to anticipate.
It really is. Something to keep an eye on for sure. Thank you for joining us on this deep dive.